Yeah, hello everyone. My name's Shane Kumpf. I've got Billy Rinaldi with me down here in the front row. We're members of the YARN R&D team at Hortonworks. We're also Apache Hadoop committers, and we're here to talk to you today about containers and big data. So before we really get into the topic, I want to level set. So at Hortonworks, we run many different tests, right? We have dozens of product releases happening each year, over 30 different open source projects that make up our stack across a dozen different Linux operating systems and multiple backend databases. As a result of all those permutations, we run tens of thousands of tests every time we do a release. You probably already knew that, but what you may not have known is we're doing all of this on a container cloud powered by Apache Hadoop YARN, right? So you heard me right, we run HDP in Docker containers on top of Apache Hadoop YARN. And we've been doing this for over 2 years now, right? 2 years and 7 million containers later, we really learned a lot of real-world lessons, and that's what we're here to talk to you about today, some of those real-world lessons. Before we really get into the intersection of big data and containers, I want to step back and talk about the evolution of containers and the evolution of big data. So when we talk about containers, right, they're really starting to gain momentum. There's this industry adoption is continuing rapidly. We have these patterns emerging, things like multi-cloud and hybrid cloud strategies, the ability to deploy the same way both on-prem and in the cloud. The adoption of microservices, so taking these monolithic applications and splitting them down into their smallest boundaries, right? Where it makes sense to scale as well as manage those applications. And we're also seeing exponential ecosystem growth. There's dozens of container orchestrators on the market today, thousands of plugins for network, storage, policy, you name it. And we're starting to see some big market moves, new acquisitions, new players coming into the market. So really, how did we get there? How did we get here with containerization, right? So if we really think back to infrastructure, where we started with physical servers. Someone had to walk into the data center, rack this thing up. There's a very good chance your application didn't play nice with other applications. So we end up running a single application per physical machine. That's very wasteful, right? As we started to identify that problem and look at solutions, things like virtual machines came into play. Now we could take a bunch of operating system instances, put them on a single physical host, and really drive utilization, simplify IT, and really drive that business agility. And if we think about containers, it's really about that pursuit for faster, better, cheaper, the IT mantra, right? And it's really just an extension of what we did with VMs. As we started to look at VMs, there was inefficiencies there as well. There wasn't a lot of reuse as far as software assets within VMs. Beyond that, you had the operating system overhead from every one of these virtual machines. So what if we could get rid of that operating system overhead and give that to applications, right? Quit wasting those resources on something that could be used better with our applications. And that's exactly what happened with containers. So this is really why they're gaining popularity. They improve hardware utilization through increased density. Again, we remove that virtual machine operating system overhead. We no longer have to have an operating system per instance. We can now all share that operating system kernel, right? That single kernel. And we can also start to reuse assets on disk. So consider an application where you have 10 different applications, they all depend on the same underlying CentOS 7 libraries, right? We can store those once on disk and then reuse those across our applications. You also get strong resource isolation through things like Linux kernel features like namespaces and control groups. There's better software packaging, and this is really a big one, right? We can package applications and dependencies together, okay? So think about a complex application, maybe a Python application, right? That has all of these different dependencies that you need to include. How we did this before containers is the admin had to install that software on all of your different systems. It was very hard to manage. With containers, the developer now has the ability to define those dependencies as part of that image. And also, there's a great distribution mechanism that comes with containers as well. So in the Docker world, we have something called a Docker file, which is essentially infrastructure as code. We can define what are the libraries that need to be included with my application, as well as the application itself. And from a distribution mechanism standpoint, I can now share that Docker file with anyone in this room. And I could even share the actual image with anyone in this room. So it's a very easy way for me to share with coworkers and the public the work that I'm doing. And as I mentioned, you really get some improved developer self-service out of that, more control over that execution environment. It's now up to the admin to determine what dependencies they need and then define that. And so we're starting to see some patterns emerge as a result, right? This mix of services. You have both long-lived services next to your ephemeral jobs. Now, I will mention that the container market is mainly focused on services to date, while there has been some work done around jobs, not in the traditional big data sense. We're seeing more of a decoupled compute and storage model that allows people to scale those tiers independently. And we're starting to see that desire for hybrid deployments. I want to deploy the same way I do on-prem and in the cloud. And containers can really help with that. So having level set on containers, let's step into talking about big data as well. When we look at it, big data followed a very similar pursuit, right? That pursuit for faster, better, cheaper, the IT mantra. So we started with these siloed systems, your ERPs, your CRMs, your EDWs, maybe some departmental data marts. And we really needed to start to knock down those silos so that we could start to get insight across all our data. And we also needed to do it at a much cheaper price point. You know, if you look at those traditional engineered systems, they're very expensive, but we needed to, they were no longer financially feasible when you're talking about the scale of big data, right? So that's really where Apache Hadoop came from, massive scale, more efficient than those siloed systems. Again, very much that same journey that we see with containers. But what really made big data popular was that store and process cost effectively at unprecedented scale, batch and interactive workloads on shared infrastructure, multi-tenant resource allocation capabilities, and a scale-out architecture. Of course, Hadoop is much more today, right, with things like security and governance, BI tooling, operational, ML, AI, streaming, the list goes on, right? There's not much you can't run on this platform today. But really at its core, big data is two things. It's a platform and a collection of workloads, right? And when we're talking about workloads, this is the user-defined jobs that run on the cluster. So the user says, I need a container with this amount of resources to schedule on there. The containers get horizontally scaled across these physical nodes, and the platform schedules those containers. Now on the platform side, it's the one that manages all of the resources in the cluster for running those workloads on top of. It includes advanced scheduling capabilities, multi-tenancy through queues, capacity guarantees, et cetera, as well as the fine-grained scheduling. So really at its core, that's what a big data platform is made up of. And there's also multiple classes of application type when we're talking about big data, right? There's things like jobs. These are your batch and your interactive workloads, those short-lived ephemeral type workloads. There's services, which is your long-lived services, those persistent services. And then on the platform side, this is really the plumbing for those workloads, right? It's the schedulers, the orchestrators, the resource management pieces. But what's really unique to big data workloads is that these platforms understand data locality, right? They know how to move your workload closer to where the data lives, which is very important for some types of workloads. The other thing I'll point out here is the lines may actually be blurred as you look at these different classes of applications, right? Let's talk about something like Hive. So Hive, you submit a SQL query. You could argue that's a job, right? However, Hive also maintains an in-memory cache. It has some, it benefits from being a long-running service, right? If we can have these containers run longer, we get better performance out of it. So you could say it's a service. At the same time, there's a lot of sharing between tasks, right? They need to communicate between each other. There's plumbing, things like the Metastore, Hive Server 2. At this point, you know, Hive even starts to look like a platform, right? So where do you really draw that line between job services, platforms, et cetera? And it's very difficult to do. But to kind of level set on what we're talking about today, these are the types of things we're looking at as far as these different types of systems, right? When it comes to jobs, we're looking at things like MapReduce, Hive and Tez, the Spark Core. Long-running services is things like HBase, Spark Streaming, Storm, LLAP. And on the platform side, we're looking at things like Yarn, Kubernetes, some of the cloud services, et cetera. So having kind of level set on both of those, I want to talk about containers and big data together. And really, it's one slide. It's complicated. I know nobody likes that answer, but there are many nuances depending on your workloads here, right? As I kind of mentioned, workloads can be platforms in disguise. There's varying requirements on co-location, right? You may want two services running together, or you may want two services that can't run together, right? So being able to figure out where those get placed within the cluster is very important, and it's very workload dependent. There is no one size fits all. There's different levels of containerization, from fat containers to microservices, and we'll talk a little bit more about that. And which route you go changes the amount of complexity. And really stepping back, you know, this is a very similar discussion that we'd have between big data and VMs. You know, don't just containerize to containerize, containerize with a purpose. Like, what are you really gaining by moving to containers with this? So that's some things to keep in mind when it comes to big data and containers. Oops. So now I want to move into some general considerations. We talked about the fact that yes, it's nuanced, not one size fits all when it comes to containerization. So let's talk about some of the things that you should be considering as you start to move towards containerization for some of your applications. What we're going to do is talk about some general considerations that aren't necessarily focused on big data, just things with containers. And then we'll go into each of those different application types and give you some details about the considerations there, plus some demos. So on the general considerations side, there's really 4 things we want to talk about today. Things like operating system stability, fat containers versus microservices, stateless versus stateful apps, and then your networking side. When it comes to system stability, understand that containers are really just an extension of the OS kernel, right? It's features within the OS kernel that are being exposed through containers. So what you need to understand is these are very advanced features. They didn't exist in the kernel that long ago, and there's a very good chance that the kernel you're running may not include them. So there's very poor support for many of these features in a lot of the kernels, and really one container can cripple your host, right? If you run into a kernel bug that panics that system, everything on that system's gone, right? So you have to be very careful about the types of workloads and really test things out. And ultimately, you need to run the newest kernel. We have gone through about 4 different kernel iterations, and we're now running a 4.15 kernel, if that tells you anything. That is the newest, latest, greatest EL repo kernel, because we need these features to be stable. Another thing that's very important is the Docker storage driver. So when you allocate a container on a system, the root file system is stored using this storage driver. Out of the box, there was one called Device Mapper. It's since been changed, but that used to be the out-of-the-box default. With things like Device Mapper, heavy writes to that root file system. If somebody spins up HDFS in your container and starts writing to the root file system, it's just going to kill that machine, right? I/O weight goes through the roof, and it's just not going to run very well. In those cases, you may actually even need SSDs backing that file system. But what we would recommend is use overlay 2 if your workload allows it. So you need to do some testing. Overlay 2 is much more performant. However, it's not compliant, so it doesn't work for all systems. So you need to keep that in mind. So moving on from that, I want to talk a little bit about fat containers versus microservices. So what we're seeing as a good intermediate step for bringing in containerization is something called the lift and shift model, which is containers as VMs, right? You need some sort of an init system running in those. And essentially, we're just going to act like we're going to take this VM with all of its software, and we're going to move it into a container, right? It's, again, just lifting and shifting it over. And it's going to look very much like a VM. It'll have an init system. If you're running something like systemd in a container, that's something you really need to be careful about. Systemd is... It expects to own the system, and it'll do things like start creating mounts. It needs to run as PID1. Newer versions of systemd actually won't even run as non-PID1 in system mode. So you need to really be careful about what that init system is. And the reason for an init system is inside this container, the process space is owned by that container. You need something at the top, PID1, right, to do all of the reaping of those the zombie processes. And full decomposition is really a journey. There's steps in between, and what you ultimately need to look at is what are you gaining by breaking these down, right? If we step back just a couple of slides here, there's a couple of examples of what this might look like if you did full decomposition versus just fat containers. And as you look to the right, yes, it's a nice model, but what are your scaling domains? What are you really gaining by breaking up Hive into that many levels, right? This intermediate step might be the more appropriate solution, but you need to test and understand for your workloads. Moving on from fat containers and microservices, we have state and stateful applications. So ideally, stateless applications are really what work well with containers. They're easy to scale. We can have multiple backends. If a backend dies, we can just change a load balancer. Makes it very easy to work with when you're not dealing with the data pieces. However, what kind of state do you need to actually store within that container or deal with in that container is something you need to determine as well. If you can't go with stateless containers, there's a number of different things to consider, right? So do you need to checkpoint in memory state? What happens with this data if I write it to disk and I start another application on top of it? Can it even read this data? I mean, there's a lot to consider more than just storing some data somewhere that I can access it. And then finally on the networking side, you know, the great thing about networking is all the options said no one ever. I don't know about you, but there are way too many networking options when you look at the legacy systems, start bringing in SDN, et cetera, right? And the burden's really on you. When it comes to container orchestrators, they really push that off to the operations teams. They leverage things like the Docker CNM model or something like CNI, which are some standards around integrating with networking capabilities. Ideally, though, what you're shooting for is one IP per container, no NAT, right? We don't want any network address translation. And again, as I mentioned, most of the orchestrator systems today, they offload this responsibility to some sort of a plugin. So there's heavy use of software-defined networking in here, which can really be challenging for people that haven't worked with this type of networking before. So, you know, kind of covering some of the general recommendations now, I'm going to turn it over to Billy to let her go ahead and take you through the different classes of applications and demos. Thank you.
Can you hook up the... So, let's see. I'm going to start talking about the considerations for specific types of workloads, starting with batch, ephemeral, and interactive workloads. And the workloads we're talking about here are things like MapReduce, Apache Hive and Tez, and Apache Spark. So these are typically like analytic workloads that are going to run on top of other platforms or orchestrators. And the primary benefit for running these in Docker containers would be for packaging dependencies. So a lot of analytic workloads require you to install special libraries, jars possibly, or Python libraries. And that's going to be a lot easier to install once in a Docker image, and then push that out to your hosts as opposed to installing it on all of your hosts. The challenges for running these type of workloads in containers are data locality and networking considerations. So a lot of applications that rely on data locality are relying on the fact that the client hostname and the data node hostname are the same. So that's how they tell that a local read can be made. But when you're running in a Docker container, the Docker container will typically have its own hostname. So one way to get around this is to set the Docker network to host. And in that case, let's say the container hostname will have the same name as the host, and it will know that it's local to the data node. Another issue is user identity propagation. So if you want the analytic to run as a particular user, then you need to have the same user in the container with the same UID and group ID as outside the container. And there are various ways to approach that problem. Let's see, so can we get it switched over to this one? So we're going to try to demo from the other laptop. Hopefully we can get that set up. So the first demo we're going to try to show is a Spark demo of running a Spark Pandas UDF analytic in Docker containers. Okay. So, oh great. So if we take a look at this pandas UDF script, first we're going to import some packages, and these have been installed in our Docker image. And then we're going to generate 100,000 random rows, divide the rows into 100 different groups. And what we're going to do is run the pandas data frame group by to run an OLS linear regression model on each group, and then we'll output the results for each group. So to run this script in Docker containers, I'm running the PySpark command, telling it to run my pandas UDF example script. And I'm running this in Spark on Yarn on Docker containers. So the relevant parameters here are setting the Yarn container runtime type to Docker, setting the Docker image to our pandas demo image, setting the Docker mounts to mount etc password into the container. That's how we're handling the user issue that I mentioned before. And let's see, lastly, setting the Docker container network equal to host. So now that this is loaded up, it will have already run the script. So we can look at the original data frame, which has 100,000 rows, and the last row is the group that each row is assigned to. Sorry, the last column is the group it's assigned to. And we can take a look at our results. So for each group, we can see the model parameters. So moving on to our next type of application is long-running services. So as opposed to batch applications, the long-running services are going to be ones that are serving queries or lookups, and they may have low latency requirements. And here we're talking about things like Apache HBase, Apache Spark SQL or Spark Streaming, Apache Storm, and Apache Hive LLAP. The primary advantages of running this type of application in containers are ease of deployment and ease of scaling. So it's you can spin up new workers and spin down new workers based on your workload needs. New challenges for this type of application are client access. So typically, you'll need to have a client that's configured to know how to connect to your long-running service. And you may also need service discovery, so like a well-known URL that you can use to access your service. And then, let's see, there are also some similar considerations to batch applications, so data locality. I can talk about that a little more. For example, Apache HBase likes to do the short-circuit local reads, and there are some special considerations if you want to do that in containers. You would have to mount the short-circuit read socket into the container, and since the short-circuit reads use a shared memory segment, you would also likely have to set the IPC namespace of the container to shareable. Other issues for long-running services are token key expiration and renewal in secure clusters, and generally management for the long-running service. So like, what if you want to change a configuration and restart the service, or upgrade the service to an entirely new version? And monitoring the service are other things that are specific to this type of application. So in this case, I'm going to demo HBase running as a long-running service on Yarn. And to save time for the demo, I've already started this service running on my cluster. We can see it's this HBase app 1. I have 1 client container, 1 master, and 3 region servers. For the demo, what I'm going to do is flex this up to 5 region servers so we can see how easy it is to do the vertical scaling. Let's see. If I reload this, it's already, the service already knows it should have 5 region servers. If I go to the HBase master UI, it'll take it another minute for the region servers to come up and register with the master. But you can see these, the original 3 region servers have registered with the master with well-known host names that are defined by the Yarn service framework. So that's component name, followed by service name, followed by user, followed by domain. let's see, we could look a little bit more into the service specification that's used to create this HBase app. Let's see. So some interesting things here are, again, we have the Docker mounts mounting etc password, so we get the consistent users in the container and outside. And in this case, we're creating some configuration files that are sort of enhancing the base Docker image with some additional configuration for running the HBase app. And lastly, we're publishing the master UI. So if we go back to the master, by now we should see the additional 2 region servers have connected. So the last type of application we're going to talk about are platforms. So platforms are typically running workloads. And the challenge there is platforms usually expect to own the entire system. So that's why it's harder to containerize them. And for the types of things, types of applications there, we're talking about Yarn, Kubernetes, Docker Swarm, Nomad, Mesos, etc. Some benefits to containerizing platforms are getting better hardware utilization, leveraging an existing investment into one platform for being able to run applications on other types of platforms as well, and for developer environments, so you can try out running new types of applications. Challenges there are resource sharing, and again, some of the same challenges as we had for other applications. But actually, platforms are so complicated, we have an entire other slide for talking about their challenges. So if you're talking about Yarn and Kubernetes, running 2 schedulers gets to be very complicated. So for one, you have to decide what you're going to do. Are you going to run Yarn on Kubernetes or Kubernetes on Yarn, or maybe run them side by side and have some elastic resource sharing between them? And when you're running platforms on platforms, you're talking about not just running the platform itself, but all of the children, all of the jobs that platform is running also have to be considered in the resource sharing. So one thing we've worked out is, as far as resource sharing, is a sort of hierarchical C-group mechanism. So both Yarn and Kubernetes use a sort of a parent C-group with C-groups for each child container inside that C-group. So if you're running a platform on top of a platform, you could have the container C-group be the parent of the child platform. So for running Kubernetes on Yarn, for example, you can have the Kubernetes parent C-group be the Yarn container C-group, and then any pods that are run by Kubernetes would be inside that Yarn container C-group. So that would let you sort of limit the resources run by the child platform, but to change the amount of resources used by each, you would have to do something like possibly just add new containers for the child platform, or remove them to just adjust the total amount of resources it's using, or possibly resize the containers. On the storage side, as far as storage sharing, data nodes are not very movable, and storage isn't an elastic resource. And I/O bandwidth is more shareable, but big data applications typically sort of need their own dedicated I/O bandwidth, nevertheless. So as far as running data nodes and Yarn workloads and containers, at this point, you're probably going to end up using fat containers if you're going to run them in containers. So for this demo, I'm going to show Kubernetes running on Yarn as a long-running Yarn service. Again, I have already started up the Kubernetes application. Let's see. So if I go into services and look, I have 4 kubelets and 1 Kubernetes master. To look at the specification that I used to create this service, we have some new requirements that were specific to Kubernetes. Well, actually, for any platform that's going to do things with C groups, for it to let's say, be able to write the process IDs of the child tasks into the C group properly, you need to set the Docker PID namespace equal to the host PID namespace. There are also a much larger list of Docker mounts that are required by Kubernetes, which are related to sort of the platform thinking it owns the entire host. And in particular, I'll highlight to allow Kubernetes to run Docker containers, we're mounting the Docker socket into the Kubernetes container. And that's what allows the Kubernetes running in a container to run Docker containers on the host. Oops. So again, we have the Docker network equal to host for Kubernetes. And in the master, it's the master component here is starting up a kubelet, and then all the manifests for the Kubernetes master processes will be placed into the manifest directory for that kubelet. So it'll start up the Kubernetes API server and all the other Kubernetes masters. And then, let's see, we're also starting a Kubernetes dashboard on the master. And then there will be 4 other worker kubelets. So if we go to the dashboard, we can see we have the 4 kubelets and the Kubernetes master that are connected to this Kubernetes instance. And you can see the host names are in the YARN service framework format, the host names that are created for those Docker containers. So here we're going to run a simple HTTP service on Kubernetes on YARN. And this is going to have 2 replicas of a simple HTTP service. There's going to be a Kubernetes service called the HTTP service, and there'll be 1 client. And what that is going to do is connect to the named HTTP service and then just output whatever it gets, which should be hello from hostname. So if we reload that, the client should be completed, and if we take a look at its logs, we can see that it said hello from HTTP service. So this is a pod that ran successfully on Kubernetes running on YARN. And so this is the Kubernetes on YARN approach. There is also the approach of running Hadoop on Kubernetes, and there have been a number of other talks at the conference, which actually already happened earlier in the conference, so you'll have to look them up online if you missed them. So in summary, what we're trying to say is that there's a lot of nuance here. Basically, each application that you try to containerize is going to have its own considerations. And there'll typically be a lot of benefits, but you also have to understand if you're giving anything up by running them in containers. And let's see. Thank you to the Apache Software Foundation, without which probably none of us would be here. Any questions?
There's a mic up here if you wouldn't mind. Just so they hear it.
Hi. Not all that familiar with Docker or Kubernetes, but you mentioned something earlier about config changes. Would I be able to, for example, if I were deploying YARN on YARN through a container, you mentioned that's probably not the best idea, but one of the things that stands out to me is that if I have to change a queue and I need to modify a config file like a capacity scheduler XML, how do I deploy a config change into an already running container? Is that something that can be done, or?
Let's see.
That's just one example, but.
Yeah, I mean, I think things like that are possible. In Yarn, for Yarn long-running services, we're starting to do a little work on upgrades, but it's not complete yet. So we still have some work to do there, but the goal would definitely be for you to be able to provide a new configuration specification. Possibly I would look for that functionality in 3.2.0 or beyond of Apache Hadoop.
But it sounds like maybe just start off to be a little less ambitious and look to some of the job-oriented things like the map reduces and not necessarily jump all the way to a Yarn.
Let's see. Yeah, I mean, I think for other types of long-running services, that is definitely ready to try out in Hadoop 3.1.1. But some services are more complicated than others, basically.
All right.
Yeah.
Thank you.
And I guess I'll add, in a lot of cases, containers are fairly immutable, right? I deploy this. I'm not making a lot of configuration changes, but there's a lot of stuff in the Yarn Native Services API that makes it pretty easy to define this configuration up front. So you can actually take information from the host configuration, populate it into the container, and then override the settings that matter for your container. So there's some flexibility there. Any other questions? Yes. Oh, go ahead. It's a race.
Hi. I see that you are sharing the Docker socket file while you are running the Kubernetes in Yarn. So you are basically doing Docker inside Docker, correct?
Let's see. Actually, so Docker in Docker would actually be having a Docker container and then running a separate Docker container inside. In this case, we're reaching outside of the Docker container and launching a pure Docker container. So the second container isn't running inside. It's
so
alongside.
My question is then why you need to share the socket file?
Let's see. Yeah. So that's why you need to share the socket to. So there is a Docker and Docker capability, but it's not. It's an anti-pattern. It's not recommended to run containers inside containers. By sharing the socket, that lets us run additional sibling containers as opposed to having them be nested inside each other. And that's a lot more stable, basically.
Yeah, slight nuance. There's mount the Docker socket, or there's true Docker in Docker, which is run an entire daemon inside of a container. Right?
Yeah.
So this actually piggybacks off that question. In the Kubernetes example, considering all of the mounts and the Docker socket mount, is it feasible that if you had Kubernetes running on the host that Yarn was on, that Kubernetes would have access to the pods that were deployed in the Kubernetes that was running on top of Yarn?
Yeah, actually, I forgot to show in the Kubernetes specification that we're actually spreading it out so there is only one kubelet per host using Yarn placement policies. So I think currently where we're at, you would really only want to run one per host. But I'm starting to look into whether it would be possible to do something to run more than one per host to maybe not mount quite so many things and change some of the flags. So you could have more than one, but I'm not sure whether or not that will work out yet. Yeah.
With system Ds? So you basically have to run it as PID1. If you want system D to act right, you got to run it as PID1. So we've done some work around supporting entry points in CMD so that you can make that happen. Yep.
Thanks, everyone.
Yep. Thank you.